All right, folks, welcome back. We are in Chapter 6, Section 5 again. We're just going to wrap these notes up with inverse trig functions. It should be relatively quick. If you got your unit circle handy, that might help you out at the beginning here. Then we'll finish up with a word problem. So here we go. So we're just going to work our way inside out of these compound trig function versus inverse trig function problems. Okay, the sign of negative pi thirds is negative radical 3 over 2. Okay, and now we're just taking the arc cosine of negative radical 3 over 2. So which angle has a cosine of negative radical 3 over 2? That has to be in quadrant 1 or 2, and that's going to be 5 pi 6, or 150 degrees. Okay, 150 degrees. Now the next one, the arc sine of 1/3. Okay, again, that's a ratio that is not a special ratio on our unit circle, so we're going to have to use our calculator. Okay, the arc sine of 1/3. Beautiful. And now I've got to take the secant of it, which means I have to take the reciprocal of the cosine of that. So I'm simply going to 1 divided by cosine of that value. Close it out. And the secant value is 1.06. Okay, moving on, the arc cosine. So what angles in quadrants 1 or 2 have a cosine value of negative 1/2? That is going to be a special ratio on our unit circle. That is going to be 2 pi thirds. Okay, and we're just taking the cotangent of 2 pi thirds. So if the tangent of 2 pi thirds is negative radical 3, then the cotangent of 2 pi thirds is going to be negative radical 3 over 3. So again, with your unit circle, that can help you out. Okay, here we go. Evaluating the cosine of 135 is going to be negative radical 2 over 2. So the arc sine of negative radical 2 over 2 is going to be what values in quadrants 1 or 4 have a sine value of negative radical 2 over 2, and that's going to be negative pi fourths. Easy peasy. Okay, keep going here. The sine of pi thirds is going to be radical 3 over 2. What angles in quadrants 1 or 4 have a sine value of radical 3 over 2, and that's going to be pi thirds. You see something unique happen there. It's not always the case, but it is sometimes the case when you take the arc sine of the sine of an angle, as long as that angle itself is in quadrant 1 or 4. Anyways, arctangent of negative 1. What angles in quadrants 1 or 4 have a tan value of negative 1? It's going to be negative pi fourths. The tangent of negative pi fourths is negative 1. Okay, so you see kind of the same thing happening there as well. So let's go ahead and jump down into slightly more difficult problems here, where we're being asked to find the arc sine of negative 11/61, and then the cosine of that. Okay, and let's pretend that we don't have a calculator now. Okay, so if we don't have a calculator, I know that if I'm taking the arc sine of an angle, it's going to be in its negative angle, or negative ratio, it's going to be in quadrant 4. Okay, opposite over hypotenuse, negative 11 over 61. Pythagoras would tell us that our adjacent side here is 60. Okay, now the arc sine of this ratio, negative 11 over 61, is giving us an angle, and it's going to give us, this angle theta, which would tell us this large angle if we wanted it, but we don't really care because we're trying to find the cosine of that angle. Cosine of that angle is adjacent over hypotenuse. It's going to be 60 over 61. Really simple. So let's do another example just like that. Okay, so we're trying to find the arc cosine. We have a positive angle here, or a positive ratio, so we know that our angle is going to be in quadrant 1. Adjacent over hypotenuse. Adjacent over hypotenuse. And a little bit of Pythagoras would tell us that this is 4x squared minus 25. Pythagorean theorem. That's all we're doing there. Okay. Now again, the arc cosine of a ratio is giving us an angle, and it's going to tell us what this angle is right here. However, we don't care what that angle is. We're trying to find the tangent of that angle, which is opposite over adjacent, which is going to be the square root of 4x squared minus 25, all divided by 5. Super simple. We're just evaluating ratios of angles. We don't necessarily care what the angle is because we're taking the tangent of that angle. So the exact same thing's going to happen here. Okay, so here we see arc secant, something we've never seen before, but we can infer that it's going to be hypotenuse over adjacent. It's going to be a quadrant 1 angle. Because this ratio is positive, if it was negative, it'd be over here in quadrant 2. But hypotenuse, 9 plus x squared over adjacent, x. And if you did a little Pythagoras, a little bit of simplifying, you would get the height to be 3. Again, the arc secant is telling us this angle theta right here, but we don't really care what that theta is. We're taking the tangent of it, opposite over adjacent, 3 over x. Okay, we're on the back now, and the first word problem is talking about winter avalanches and how they occur. So one of the reasons is the slope of the mountain. So avalanches seem to occur most often for slopes between 35 and 60 degrees. Okay, the slopes at a local ski resort have an average rise meaning vertical, of 2,000 feet. For every horizontal run, 2,559 feet. And we want to know, is this angle of elevation, theta, going to put us in a danger of an avalanche? So let's find out what theta is. We want to solve for an angle, we better be using our inverses. I'm going to go ahead and use the arctangent of 2,000 over 2,559. That way I don't have to worry about Pythagoras and finding my hypotenuse. Okay, now I'm just going to take the arctangent of 2,000 divided by 2,559, hit enter, and that tells us that we're about 38.01 degrees angle of elevation or rise on our ski slope. So yes, we are prone to avalanches because we're between 35 and 60. Okay, the last question here is about a soccer player on a breakaway and dribbling just inside the right sideline toward the opposing goal. So as the defense closes in, she has just a few seconds to decide when to shoot. You can see kind of the diagram, okay? And you can imagine how angle theta is changing as the soccer player gets closer and closer and closer to the end line here, the line that the goal is on, okay? So we want to find an expression for the shooting angle theta. Okay, because eventually we're going to want to find out when is theta going to be the biggest, so that that soccer player can determine when to shoot the ball. Okay, so an expression for that angle theta, well, we want to find this small angle theta. We're going to use some logic here and say it's this big angle here minus this smaller angle here, because both those angles that I just drew are both part of giant right triangles. So theta, if we're trying to find theta, we're going to be using inverses, and I'm going to be choosing to use inverse tangent because I know my opposite and I have a variable adjacent that is changing, d. Okay, so if we're talking about the big angle first, theta is going to be big minus medium is going to equal small angle theta. Okay, so big angle, inverse tangent of 94 divided by d. Okay, is going to give us this really big angle that I keep drawing with my pencil here. Now we want to subtract off this angle here that I'm drawing with my pencil. Okay, and that'll leave us with whatever angle theta is. So we're going to subtract off. And I'm going to use arctangent again because I know the opposite. It's going to be 70. And I've got the same variable adjacent, d. Beautiful. And there's my expression for theta. Theta is going to be whatever angle is this angle minus this angle, or big angle minus this medium angle. It's going to give us small angle theta. So in order to determine that distance, we're going to maximize our shooting angle, we're going to actually graph that equation that we just made. So if you look, I've put it into my y equals, already, and I can do a zoom 0, and what should happen is it will scale the graph so that I can see where the maximum on this graph is. And then we'll do a second calc max, and it'll tell us how far away we should be shooting our ball and what the maximum angle will be. So we can see here's our graph. You see it's going up and down. Clearly we don't care about negative distances, okay? So we don't care about the left side of our graph, but there's our maximum that we care about. So to find that maximum, we're all going to press second calc, which is this trace button right here, and we are going to go down to max, and we're going to select maximum, and our crab just needs to be to the left of our maximum, and our little crab, starfish, whatever you want to call it, now it's saying what's the right bound. We'll go to the right of our maximum. You can guess if you want. I don't usually guess, I just hit enter, and you can see right there, okay, that when we are 81.11 feet away, we will have a theta that is 8.41 degrees. And that's the absolute maximum biggest angle that the soccer player will have to shoot on goal. If they go any closer to the baseline here, then that angle is going to get much smaller and have less of a chance of making it. That's Chapter 6, Section 5. Thank you so much, and see you tomorrow.